Respiration. In this module, you will learn how to calculate consumption and autonomy and how to breathe at depth. You will also learn more about hypercapnia and nitrogen narcosis and how to avoid and resolve it. Consumption of the breathing mix. The deeper the dive, the less autonomy the breathing gas provides. The regulator provides air at ambient pressure. Even though a diver maintains respiration at a constant volume, as the ambient pressure increases, so do the normal liters consumed with every breath. With an increase in pressure, the number of molecules contained in a predetermined volume also increases. This is the density. The increased density is also the cause of the greater respiratory effort that the diver needs to make at depth. Breathing gas consumption depends on various factors, such as the diving activity, physical fitness, emotional state, water temperature, etc. But it can be estimated, as you learned on the PSS Advanced Open Water Diver course. So two important problems arise with an increase in depth: having enough breathing mix for the dive and knowing how to manage it so it does not run out. This is why we are going to repeat some of the concepts. Remaining autonomy and surface air consumption rate. The simplest method of calculating the remaining autonomy on the dive, the calculation of the pressure variation in a unit of time, or rather, determine the bars a minute, pounds per square inch a minute. Imagine that you are at a certain depth and you look at your pressure gauge and it reads 180 bar, 2,700 pounds per square inch. After 10 minutes of the same depth, you see that the pressure gauge indicates 120 bar, 1,800 pounds per square inch. If you remain at the same depth, how long will the air in the cylinder last? It is easy to work out that the remaining autonomy is 20 minutes. In fact, having used 60 bars, 900 pounds per square inch in 10 minutes, the consumption rate is 6 bars a minute. 60 divided by 10, 90 pounds per square inch a minute, 900 divided by 10. So the remaining 120 bars, 1,800 pounds per square inch of air, is enough for 20 minutes, 120 divided by 6, 1,800 divided by 90. This figure of 6 bars a minute, 90 pounds per square inch a minute, is only valid at that particular depth. In order for the figure to be more meaningful, we need a reference depth. For divers, this is the surface. In practice, you must calculate how much air you would breathe if you were breathing in the same way on the surface. This is the surface air consumption rate, abbreviated to SAC. Just divide the consumption calculated on the dive by the absolute pressure at that depth. If, for example, the depth at which you worked out the figure of 6 bars a minute was 20 meters or 66 feet, 3 atmosphere absolute, the surface air consumption rate is 2 bars a minute, 6 divided by 3, 30 pounds per square inch a minute, 90 divided by 3. Using your personal surface air consumption rate, you can work out your consumption at any depth by just multiplying it by the absolute pressure. Respiratory volume per minute. Surface air consumption rate, minimum reserve. The variation in consumption with the depth is due to the fact that with a constant respiratory rhythm, we breathe different densities of gas depending on the depth. The constant factor, if physical activity remains the same, is the volume of air breathed in 1 minute, which has been defined as the respiratory minute volume, RMV. A diver with a respiratory minute volume of 20 litres a minute, quarts a minute, breathes 20 litres of air in 1 minute, quarts a minute, whatever the pressure. It is the normal litres that change. The respiratory minute volume is not always constant, but varies with activity. It can fall by half if the diver stops and more than triple with physical exertion. To calculate the respiratory minute volume, just multiply surface air consumption rate in bar a minute, the surface air consumption rate in pounds per square inch a minute, divided by 15 by the cylinder capacity. If with a cylinder with a capacity of 15 litres, quarts, you have a surface air consumption rate of 2 bars a minute, 30 divided by 15 pounds per square inch a minute equals 2. The respiratory minute volume is 30, 2 multiplied by 15 litres a minute, quarts a minute. The surface air consumption varies depending on the cylinder being used. This is because only the respiratory minute volume remains constant. To calculate the new surface air consumption using the metric system, just use the formula surface air consumption equals respiratory minute volume divided by cylinder capacity. With a respiratory minute volume of 30 litres a minute, using a cylinder with a capacity of 15 litres, we have a surface air consumption equal to 2 bars a minute, 30 divided by 15. Instead, with a cylinder of 10 litres, the surface air consumption becomes 3 bars a minute, 30 divided by 10. With the imperial system, you must use the tank factor that enables you to pass from surface air consumption to respiratory minute volume in cubic feet a minute. This is equal to the ratio between the volume of the cylinder and the pressure at which it is measured. For example, in a steel cylinder of 96 cubic feet at 3,300 pounds per square inch, it is 0.02909, 96 divided by 3,300. So the surface air consumption of 90 pounds per square inch a minute can be converted into a consumption of 2.62 cubic feet a minute. This is a constant figure on the surface, linked to the respiratory volume minute. Changing to an aluminium cylinder of 80 cubic feet at 3,000 pounds per square inch, the new tank factor is 0.02667, 80 divided by 3,000. To calculate the new surface air consumption, divide the consumption in cubic feet a minute by this factor. The result for the example is 113. 2.62 divided by 0.02667 pounds per square inch a minute. Now the surface air consumption is known, it is easy to calculate the minimum reserve. Just multiply the surface air consumption by the absolute pressure and then calculate the number of bar needed to stay there for 10 minutes. Breathing at depth. On a dive, heavy breathing may demand more breathing gas than the regulator is able to provide, so respiration becomes inefficient. The inability to regain normal respiration underwater may lead to panic and the serious consequences it involves. So, at the first symptoms of breathlessness or heavy breathing, you must stop, rest, and wait until your breathing returns to normal before continuing. To prevent this happening, a fundamental rule for deep diving is to breathe more slowly and more deeply than normal. The fact that you have to breathe more deeply is valid for all diving activities. due to the use of certain items of equipment that increase the dead air spaces. Breathing slowly becomes more important the deeper you go. As the depth increases, the density of the air in the hose and the second stage also increases. In respect to the surface, on a dive to 40 meters, the density of the air that passes through the hose increases by 40%, while that in the ducts of the second stage becomes 5 times greater. This increase in density creates a need for greater respiratory effort, and this may even be greater than the sum of the increase in density because in some areas the laminar airflow becomes turbulent and creates a sudden increase in the resistance to the flow of breathing gas. Luckily, the effort with both the laminar and the turbulent flow is proportional to the square of the speed of the flow. This means that by halving the speed, we can reduce the effort by a quarter and compensate for greater respiratory effort caused by the increased density. Carbon dioxide. Carbon dioxide is also known as carbonic acid gas, or by the obsolete term carbonic anhydride. Carbon dioxide is a colorless, odorless gas. Its chemical formula is CO2, and its normal concentration in atmospheric air is 0.04%. Carbon dioxide is a waste product of our metabolism, then of respiration, however. Its concentration in the body is the means by which the brain perceives the need to breathe. An excess of carbon dioxide in our body can, however, cause serious problems. Hypercapnia. Hypercapnia is a situation in which there is an excess of CO2 in the body. This may be caused by inadequate ventilation, holding your breath, excessive physical exertion, or excessive respiratory effort caused by the poor performance of a regulator. 10 minutes at a partial pressure of carbon dioxide at 0.02 atmosphere produce an increase to the respiratory rate. At 0.03 atmosphere, breathlessness begins, followed by a headache, nausea, tunnel vision, and mental confusion. Between 0.08 and 0.1 atmosphere, there is a feeling of weariness and a loss of consciousness. For this reason, the partial pressure of carbon dioxide should be less than 0.005 atmosphere. Even breathing a gas mix with no carbon dioxide in it, we will find it in our breath anyway, because our organism produces it. Carbon dioxide is an essential element for life, because it is one of the main elements by which breathing is controlled. There are, in fact, types of chemical probes that induce an increase to the breathing rate if the level of carbon dioxide in the blood rises. An excess of carbon dioxide may also be caused by breathing a contaminated air supply, contamination that may even involve the dangerous gas carbon monoxide. Preventing carbon dioxide accumulation. A headache after a dive is very often a symptom of carbon dioxide accumulation. Many people think they can deal with hypercapnia by getting used to it, but in reality you only get used to tolerating sudden changes to carbon dioxide levels without activating the defensive mechanisms, so therefore worsening the situation. In order to reduce the accumulation of carbon dioxide, you must follow the 3 fundamental rules. Breathe continuously, slowly, and deeply. Do things calmly and do not exert yourself on a dive. Choose high-performance regulators and ensure that they remain so with time by having them periodically serviced by an authorized specialist center. In case of excess carbon dioxide, it is very important to act quickly to help the diver. A diver who loses consciousness after an excess of carbon dioxide is quickly revived if his or her lungs are ventilated with fresh air. Nitrogen. Nitrogen is a chemical element with the symbol N. Its molecule is composed of two atoms, N2. It is colorless, odorless and tasteless and makes up about 78% of the Earth's atmosphere. Molecular nitrogen is also inert gas, meaning a non-toxic gas that does not react or only to a minimal degree with other substances. Although inert, nitrogen is indispensable as it dilutes the oxygen in the Earth's atmosphere, making the air breathable. Even at atmospheric pressure, high percentages of oxygen could be toxic. Inert gas narcosis. As we have seen, in normal conditions, nitrogen is a physiologically inert gas, but breathed at sufficiently high partial pressures, it could cause inert gas narcosis. Divers can usually begin feeling its more noticeable effects deeper than 30 meters, 100 feet. In fact, the seriousness of the symptoms increase with depth. Inert gas narcosis generally causes symptoms comparable to drinking alcohol. Difficulty thinking, making judgments, and carrying out tasks that require certain mental or motory skills. It was for this reason that Commander Cousteau called the phenomenon the Martini effect, meaning that every 15 meters, 50 feet, was as if a diver had drunk a martini cocktail on an empty stomach. The onset of inert gas narcosis is fast, but recovery is just as quick. Ascending to a shallower depth, with the consequent fall in ambient pressure, immediately reduces the effects. Narcosis gives the diver an altered perception of a situation, so they could put themselves in dangerous situations without realizing. For example, it could create problems controlling the depth and make buoyancy adjustments problematic. The diver may do irrational things, such as taking off their mask, letting go of the regulator, or making an uncontrolled ascent. The serious risks related to inert gas narcosis is one of the reasons why the depth of recreational dives is limited to 40 meters, 130 feet. The precise cause of inert gas narcosis is still unknown. While it is a known fact that susceptibility to inert gas narcosis can vary widely from person to person. Acclimatization and adaptation are important, and in fact, novice divers tend to be affected more quickly than experienced divers, who are nevertheless affected but have developed skills in dealing with and recognizing the problem. Susceptibility to narcosis also varies in the same individual, because it can be conditioned by several factors, such as excess carbon dioxide, drinking alcohol, headache, anxiety, cold, and the effect of any medication taken. This means that even if a diver often reaches a certain depth without feeling the effects of narcosis, it does not mean that he or she will never feel them at that depth. You can reduce the possibility of suffering from inert gas narcosis by avoiding diving when you are not feeling fit or well, breathing correctly, not tiring yourself, and above all by staying calm. Logically, it would seem that a reduction in the percentage of nitrogen in the nitrox mixes would reduce this risk. Instead, it is believed that oxygen, when it is under pressure, also has narcotic potential, like nitrogen. Nitrox, therefore, does not eliminate the problem of narcosis. Instead, helium is a gas that does not cause narcosis, and is therefore the main gas used on very deep dives. However, helium must not be used by recreational divers, as there are other risks involved in its use, and special training which comes within the sphere of the PSS Technical Training Division is required. In the next module, you will examine the problems related to gas absorption and its release from the tissues, look at the problems concerning decompression, find out more about no-deco stop diving, and discover some interesting studies carried out by researchers about these phenomena. See you soon.